Exercise 1623 is giving you different NMR spectra, and it's asking you to draw the structure of the molecule. So they give you this molecular formula, and that's something that we've seen you can find using mass spectrometry. Right, you can compare the height of the molecular ion peak and the M+1 peak, and based on the difference in those heights, you can figure out the molecular formula. So if you're given that, you can then go and do a mass NMR, nuclear magnetic resonance spectroscopy, get a spectrum like this, and figure out how the atoms in that molecular formula fit together. And there are a few patterns that will really help you out if you know them. And so they are for these branches here. So first an ethyl branch, another for an isopropyl branch, another for a tert-butyl branch. So the splitting patterns for these are things that you're going to want to know. So we'll go through those, and then there are two other things you want to find too. So first, an ethyl branch, I'm going to put a little squiggly line for where the branch is attaching to the parent chain. And in an ethyl branch, you have two carbons. The first one has two hydrogens, and the second one would have three hydrogens. Now the splitting pattern for these orange ones, they're next to three hydrogens. So the pattern is the n+1 rule. They're going to form 3 + 1. They're going to form a quartet. So a quartet. And they should have an integration that corresponds to two hydrogens. For the blue hydrogens, these are next to two hydrogens, the orange ones. And so the n+ rule for that will be two neighboring hydrogens plus 1, n+1. That will split into a triplet. And the integration for that should correspond to three hydrogens. So if you have a quartet and a triplet in a spectrum, especially if the integrations are 2 to 3 for those, 2 for the quartet and 3 for the triplet, you have an ethyl group. That'll be one of the structures in your molecule. Okay, isopropyl group. So an isopropyl group, let's say that's where it's attaching to the backbone. In an isopropyl group, you sort of have this snake's tongue carbon arrangement. And on each of those end carbons, you have three hydrogens. And for the middle carbon, for this middle carbon, there's just one hydrogen. So here, you're going to have two peaks again. All of these hydrogens in the methyl groups, those are in one electronic environment. They are next door to just one hydrogen. So because of the n+1 rule, one neighboring hydrogen plus 1, those are going to split into a doublet. And that doublet should have an integration value of 6 hydrogens. The one hydrogen that's all by itself, it's next to 6 identical hydrogens. 1, 2, 3, 4, 5, 6. So by the n+1 rule, the splitting pattern for that would be 6 + 1, or a septet. So 1, 2, 3, 4, 5, 6, 7. And the integration value for that should correspond to 1 hydrogen. So if you ever have a septet and a doublet in a spectrum, especially with those integration values, 1 hydrogen for the septet, 6 for the doublet, you have an isopropyl group. And finally, a tert-butyl group, that's when you have a carbon bonded to the parent chain, and then 3 more carbons. And each of those carbons has 3 hydrogens on it. Now, all of those hydrogens are in the same electronic environment. They're the same distance away from everything else in the molecule, so you only end up with one signal here. there are no, if you look next door to it, there are no hydrogens on the carbon next door. So by the n+1 rule, the splitting pattern would be 0 hydrogens next door plus 1. That will be a singlet. But the unique thing about the singlet is that it will have an integration value of 9 hydrogens. So these are going to be really crucial patterns to recognize. If you have a quartet and a triplet, instantly think ethyl. Look for integration patterns of 2 and 3. 2 for the quartet, 3 for the triplet. If you have a septet and a doublet, think isopropyl, especially if you have integration values of 1 for the septet and 6 for the doublet. And if you have just a singlet, but with an integration value of 9 hydrogens, then you'd want to think, okay, probably a tert-butyl group. Finally, there are a couple other things you'd want to notice, some other patterns that you'll want to see. If you ever have a hydrogen deficiency index, if you calculate that, and remember you calculate that by taking 1/2, 2 times the number of carbons, plus 2, plus the number of nitrogens, minus the number of halogens, fluorine, chlorine, bromine, or iodine, and minus the number of hydrogens. If that number ends up being something bigger, I should say 4 or bigger, chances are you have a benzene ring. Now you may have other stuff, but you get a 4 degrees of unsaturation by getting a benzene ring. 1 degree for the ring, a second for the first, third, fourth for those other pi bonds. So anytime you have a 4 or more degrees of unsaturation, you should think benzene ring. And the way that you will confirm that is look at the spectrum. The only thing that has a signal between 6.5 and 8 is a benzene ring. So if you ever have a hydrogen deficiency index of 4 or bigger, check for between 6.5 and 8, and that is going to be your benzene ring. Okay, there are other little tips and tricks that we'll see as we go along, but these are some really essential tools that you'll want to use. It's much trickier and harder to interpret these spectra if you don't know these patterns. So let's try with this first one. So first we'll take that molecular formula that we would have gotten from mass spectrometry. Let's figure out the hydrogen deficiency index for that. So it's 1/2 times 2 times the number of carbons, so 2 times, we have 8 carbons here, plus 2, plus the number of nitrogens, which is 0, minus the number of halogens, which is 0, minus the number of hydrogens, which here is 10. So that's going to be 1/2 of 16 plus 2 minus 10, so that's 1/2 of 8, which is 4. Okay, so we already see our first one of those patterns that we were looking at before. If you ever have a hydrogen deficiency index of 4 or bigger, you should think benzene ring. And check that by looking between 8 and 6.5 on the spectrum. The only thing that has absorptions in that range would be a benzene ring. And you can see here between 8 and 6.5, 8 and 6.5, we have that confirmation for the benzene ring. So we'll draw a benzene ring. We know we have that. Now, to figure out how many branches our benzene ring has coming off of it, we'll want to use the integration values. They've given us relative integration values. To calculate the actual number of hydrogens in each of these different environments, we'll want to get the lowest whole number ratio for these and make sure that our ratio adds up to the actual number of hydrogens that we have. So the lowest number here is 9.1. So I'm going to divide all of these by 9.1. And so that gives me a 5 for this one, 2, 2, and 1. Let's just make sure that those are the actual numbers. These are definitely the relative amounts of hydrogens. Let's make sure that they are the exact number of hydrogens by adding them up. and comparing them, the total that we get from that, with the total number of hydrogens in the molecule. So 5 plus 2 plus 2 plus 1, that's 10. We have only 10 hydrogens in the molecule, so these are not only the relative numbers of hydrogens in each peak, but the exact numbers. Okay, so this peak, this benzene ring, has 5 hydrogens on it. Now, a benzene ring all by itself would have 6 hydrogens. There's 1 hydrogen on each of the carbons. So normally it would have 6. For it to stop at 5, the way it is here, the only way it could do that is if it had a branch. And so we know that our benzene ring has only 1 branch. So this is our first puzzle piece. All right, next, we have these other peaks. Here we have a triplet, and here's another triplet. Now, if you have a triplet, that means that there are 2 hydrogens next door. Remember the n+1 rule. The splitting pattern is you have 1 more spike in the splitting pattern than you have neighboring hydrogens. So if you have 3 spikes, like you do here in a triplet, then you have 2 hydrogens next door, or adjacent. And that's the same here. We have 3 spikes, and so that means we have 2 hydrogens next door to the hydrogens represented in that peak. And you'll notice that each of those peaks has 2 hydrogens on it. So here we have a carbon with 2 hydrogens on it, and we know that because of the integration value. Here we have another carbon with 2 hydrogens on it, and we know that because of the integration value. There are 2 hydrogens represented by that electronic environment. And we also know that both of these need to have 2 hydrogens next door to them. So we can get that arrangement easily just by connecting the 2. So now we know that that is another piece of our puzzle, representing those 2 peaks are 2 CH2s. So here's 1 CH2, and here's our other CH2. The 2 hydrogens on each, and the splitting pattern. If these hydrogens have only 2 hydrogens next door, then they split into a triplet, and that's what we saw, and same for the other one. All right, so that's our second puzzle piece. Let's take stock of what we've used so far, what atoms we've used so far, and what atoms we have left. So far, we've used 6 carbons on the benzene ring. So 6 carbons on the benzene ring, and 2 carbons in the ethyl group. So that's 6 plus 2 is 8. So we've used all of our carbons. We have no more carbons we can add. We've used 5 hydrogens in the benzene ring, and 4 in the 2 ethyl groups, in the two CH2 groups. So that's 5 plus 4, or 9. That means we have 1 hydrogen left. It's being represented by this last peak. And finally, we have an oxygen. So we only have 2 atoms left, an oxygen and 1 hydrogen. And there's only one way to put those together, connect the oxygen to the hydrogen. And that's our 1 hydrogen. So these are our 3 puzzle pieces, and there's only one way to put them together. The pieces that have only 1 place where they can connect have to go on the end, and the piece with 2 goes in the middle. So it connects like this, and just to make it a little cleaner, underneath, I'll write so that would be our molecule. The average person would look at this chicken scratch, these Egyptian hieroglyphics, and it would mean nothing, but you can look at it and see this molecule here. Okay, let's let's go through that same procedure. We have our molecular formula there, and that's something we'd get from mass spectrometry. We'd compare the molecular ion peak and the relative height of the molecular ion peak and the m+1 peak, as we did in the previous chapter. And the first thing you want to do is to calculate the index of hydrogen deficiency. So 1/2 times 2 times the number of carbons. We have 7 carbons, plus 2, plus the number of nitrogens. We don't have any nitrogens, minus the number of halogens. We don't have any halogens, minus the number of hydrogens, which is 14. So here that's going to be 1/2. 14 plus 2 minus 14. So that's 1/2 of 2, which is just 1. So we have one ring, one double bond, one ring or one double bond in this molecule. Now notice the splitting patterns we have. We have a septet, right? This is 1, 2, 3, 4, 5, 6, 7. There are 7 spikes in that. So a septet, and we have a doublet with 2 spikes. A septet and a doublet is one of those patterns that you would want to know. A septet and a doublet is the pattern for an isopropyl group. The septet is caused by the 6 hydrogens being around that 1 hydrogen in the middle, and the doublet is caused by those 6 hydrogens being split by the 1 hydrogen. So septet and doublet, we know we have an isopropyl group. But those are our only 2 signals. And here, and we've only used 3 carbons. We have 7. And here you'll notice another pattern that you'll want to keep in the back of your mind. And that pattern is, if you have a lot of hydrogens and very few signals, then you probably have symmetry in the molecule. So if you have a lot of hydrogens and few signals, few different electronic environments, then you almost definitely have symmetry. So if we just look at one isopropyl group, that's 3 carbons. We have 7 that we have to account for. So what if we had a plane of symmetry, and on the other side we have another isopropyl group? The isopropyl group is the only thing that we can have hydrogens on, because that's the only thing that has peaks to represent it in the NMR spectrum. All right, well, let's see. What have we used so far? In this case, we would have used 1, 2, 3, 4, 5, 6 carbons. So we would have 1 carbon left. Let's just write that down there for bookkeeping. How many hydrogens? 3, 6, 9, 12, 13, 14. So we've used all of our hydrogens. And then we have an oxygen. So we still have to use this oxygen. All right, so far these are our pieces. Now this carbon must be going in the middle. After all, neither of these can go in the middle. They only attach in one place. To go in the middle, you'd have to attach in 2 places. So now we have to think about how we would attach the oxygen and to the rest of the molecule. So we have 1 in the index of hydrogen deficiency. That means we either have a ring or we have a double bond. Based on these pieces, it does not look like we have a ring, so we probably have a double bond. But we can't form a double bond between this carbon and one of these branches, because if we did that, if we formed a double bond here, for example, that would take this hydrogen away, and that would take away the splitting pattern. The reason why the 6 hydrogens on the end split into a doublet is because there's a hydrogen there. So we can't form a double bond, and also if we formed a double bond, that would take away the symmetry. We wouldn't be able to form double bonds on both sides because we only have 1 double bond. And also that would get rid of the splitting pattern. So the only other place that we can put a double bond is between the carbon and the oxygen. And so now this is the piece that has to go in the middle. It's the only one that's connected to 2 different things. And the molecule we must have is this one. That's what you get when you put these pieces together. So a typical person sees this and it's a bunch of gibberish, random shapes, but you see it and you know the molecule that's in your sample. Okay, let's try C. So they give you this molecular formula. That's something you would get from a mass spectrum. Oh, and while we're at it, actually, there are ways you can confirm whether you have these molecules. And remember, you can confirm whether you have these using IR spectroscopy. If you had this molecule, you'd have an alcohol. That would be that smooth, broad peak between 3600 and 3200. And if you wanted to check to make sure that this is actually your molecule, you can do an IR spectrum, and you would have that sharp peak at around 1700 to represent the ketone. Okay, so in this next one, we have our molecular formula. We would have gotten that from mass spectrometry. So we'll take the hydrogen deficiency index, that's 1/2 times the number of carbons, which is 10, or 2 times the number of carbons, which is 10, plus 2, plus the number of nitrogens, which we don't have any, minus the number of halogens, which we don't have any, minus the number of hydrogens, which is 14. So that's 1/2, 20, plus 2, minus 14. It's 1/2 of 22 minus 14, which is 8. And so that's 4. Now remember, this was one of those things you'd want to remember, one of those patterns you'd want to recognize. If you ever have a hydrogen deficiency index of 4 or bigger, it means you probably have a benzene ring. And you always want to check by looking between 8 and 6.5 on the spectrum. That's the only thing that shows up, that creates a signal there, is a benzene ring. And notice, in between 6.5 and 8, we do have these 2 peaks there. Both of those are coming from our benzene ring. The benzene ring is the only structure that gives rise to signals in this area, in proton NMR. So we've got a benzene ring. That's what accounts for these 4 degrees of unsaturation. 1 for the ring, 3 for the pi bonds, so 4 total. All right, now how many hydrogens are on our benzene ring? Well, they give us the numbers of hydrogens, but those could just be relative numbers. We want to make sure that those are absolute numbers. So if you add them up, 2 plus 2 plus 1 plus 9, that gives you 14. We do have only 14 hydrogens in the molecule, so these happen to be absolute numbers in addition to relative numbers. Since these 2 peaks are representing the benzene ring, that means there are only 4 hydrogens on the benzene ring. 2 plus 2. On a benzene ring that had no branches, there would be 6 hydrogens. If we have to get rid of 2, then that means we have 2 branches, right? We have a total of 4 hydrogens on here, so 4 hydrogens need to be on here. A benzene ring with no branches has 6 hydrogens. That means we need to get rid of 2 of them. But which 2? And for that, you'd want to look at the splitting pattern. Notice you have 2 peaks for the benzene ring. Each peak represents a different electronic environment. The only way you could get 2 peaks, 2 electronic environments, is to have symmetry. So for the sake of comparison, imagine I were to take those 2 hydrogens off, and you'd have your branches coming off of there. In that case, if this is one type of branch and this is a different one, all of these hydrogens are in different electronic environments. This one at the top is really close to the square branch, but far from the circle branch. The one at the bottom is really close to the circle branch, but far from the square branch. So all of those hydrogens would be in different electronic environments, and you would get 1, 2, 3, 4 separate peaks. But we only have 2 separate peaks. And the way you get two separate peaks is to take two hydrogens off on opposite ends. Because now, even if these are different types of branches, there's a plane of symmetry. And because of that plane of symmetry, the two hydrogens on either side will show up in one signal, and the two hydrogens on the other side will show up in a second signal. So those are our two things. And notice both of these are doublets, and what that means is that there's only one hydrogen next door. And if you look at this structure, this hydrogen, go to the carbon next door to it, it only has one hydrogen next door, so it'll split into a doublet. And likewise, this only has one hydrogen on the carbon next door, so that also splits into a doublet, and so that explains our two doublets. Okay, so we know one of our puzzle pieces is a benzene ring with branches on opposite sides. Now let's look at the other peaks. We have a really tall peak. It's a singlet with 9 hydrogens. And that was another one of those patterns that you'd want to remember. A singlet with 9 hydrogens tells you that you have a tert-butyl group. So here we know that this is representing a tert-butyl group. Okay, let's think about how many atoms we've used so far and how many we have left over. So far we've used 6 carbons on the benzene ring, plus 1, 2, 3, 4 in the tert-butyl group. So we've used 10 carbons, so we have no carbons left over. So far we've used 4 hydrogens on the benzene ring and 9 hydrogens in the tert-butyl group. So we have just 1 hydrogen left over. And we have not used any oxygens, so we have an oxygen. So all we have left is an oxygen and a hydrogen. There's only one way to put those pieces together, connect the oxygen to the hydrogen, and that would be this one peak here between 2 and 5, remember, is where an alcohol hydrogen would show up in the spectrum. So there's only one way to put these 3 pieces together. The puzzle piece that has 2 branches on it has to go in the middle, and the molecule that must be represented by this spectrum would be this one right here. This beautiful work of art is what you understand when you see this, because you are a brilliant chemist. All right, next one. So here we have our molecular formula, which you would get from mass spectrometry. Oh, and also, if you wanted to confirm that this was the structure, you could do IR spectroscopy. You'd look for the alcohol. That would show up as that smooth, broad peak between 3600 and 3200. And if you had that, that would confirm that that would be a valid structure. That would support that structure. So in this next one, we've got our molecular formula that you'd get from mass spectrometry. And so let's do the hydrogen deficiency index with that. We have 1/2 times 2 times the number of carbons, which is 4, plus 2, plus the number of nitrogens, which is 0, minus the number of halogens, which is 0, minus the number of hydrogens, which is 6 here. So that's going to be 1/2 10 minus 6, and so that's 1/2 of 4, which is 2. So we have either 2 rings, 2 pi bonds, or 1 ring and 1 pi bond. So we'll have to keep this in the back of our minds and make sure that our final structure has 2 degrees of unsaturation. Okay. I think the next thing that would help us is to look at these integration patterns. So let's get actual numbers of hydrogens for those. The smallest number here is 1802, so I'm going to divide each of these by 1802. And that gives me pretty much just 1 for all of those. So 1, 1, and 1. Those are the relative numbers of hydrogens. So for every 1 hydrogen in this peak, there's 1 hydrogen in that one and 1 hydrogen in that one. Relative numbers, but to see whether they're the absolute numbers, the exact numbers, you'd have to add them up. That gives us a total of 3 hydrogens, but notice there are actually 6 hydrogens in the molecule. So these are not the absolute numbers of hydrogens in each of those environments. We need a total of 6. And to get a total of 6, we have to multiply by 2. So we'll multiply all of those by 2. Distributing the 2, we get 2 in each of these environments. So there are 2 hydrogens in that environment, 2 hydrogens in this environment, 2 hydrogens in that environment. Those are the exact number of hydrogens in those electronic environments. Okay, so we have 4 carbons. Here we have a carbon with 2 hydrogens on it. Here we have a carbon with 2 hydrogens on it. And here we have a carbon with 2 hydrogens on it. Now this triplet of triplets, that's a little tricky. The way we talked about that in class, the way that for us that would be worded on a test is, it'd be a multiplet. So, in other words, this group has hydrogens on both sides of it that are in different electronic environments. That's when you would have that multiplet. But the others only have hydrogens in one electronic environment around them. So, for example, we could take this here, this CH2, and we could say, okay, that has to have 2 hydrogens around it. Because if you had this arrangement, you have 2 hydrogens in your peak. The 2 hydrogens have 2 hydrogens next door. By the n+1 rule, that means it splits into 2 + 1, a triplet. And that's what we have. For this hydrogen here, for that carbon there, those hydrogens, again, you have 2 hydrogens with 2 hydrogens next door, so it splits into 2 + 1, or a triplet. And that's our other triplet. Finally, our multiplet makes sense if the hydrogens on both sides of it are in different environments. Now right now they're in the same environment, but consider what we've used so far and what we have left. We've used 3 carbons, but we have 4 carbons. So we have 1 left over. And now we can put that 1 on one side, and that's going to create 2 different electronic environments here and here, so that the hydrogens there split these hydrogens in the middle differently and cause a multiplet. As discussed in a previous video, how those multiplets form. Okay, now the only thing is, we've used our 6 hydrogens, so that's good. We have those accounted for. So we have 6 hydrogens in our structure, we only have 6 hydrogens in the molecular formula, but we also have 2 oxygens. 2 oxygens. And we have 2 degrees of unsaturation still to think about. Now, I put the oxygens on the left side of this molecule because this CH2, the one represented by that peak, is very shifted to the left. And remember, a CH2 normally shows up at around 1.2. But here, it's showing up way further between 4 and 4.5. And the only way it could do that is if it had oxygens nearby. Now, normally it's at 1.2. Here we've added around 3 to that. And the only way you'd add 3 is if you had an ester. When an ester is alpha to a carbon, the hydrogens on that carbon get shifted over 3 parts per million. So that would give us around 4.2, which is around where that is. So the shift tells us how to arrange these oxygens. Now that helps a little bit because that takes care of one of the degrees of unsaturation. We need either 2 rings, 2 pi bonds, or 1 ring and 1 pi bond. And now we have a pi bond. So now we just have to think about how to include one more degree of unsaturation. Okay, let's step back, take stock. What have we used so far? We've used 1, 2, 3, 4 carbons. There are only 4 carbons, so we've used all of our carbons. We've used 3 plus 3 is 6 hydrogens, and there are only 6 hydrogens, so we've used all of our hydrogens. And we've used 2 oxygens, and there are only 2 oxygens, so we've used all of our oxygens. In other words, we've used all of our atoms. We've taken into account the splitting patterns, the integration values, and the chemical shifts for everything. But this carbon is missing a bond, and this carbon is missing a bond. And we also have to include one more degree of unsaturation. And the way we can do that is by making this a ring. If we make that a ring, now we have 2 degrees of unsaturation, and we can connect this molecule without having any missing bonds. Oops. So first I'll draw it with a C so it's easier to follow. So there's our first CH2, our second CH2, our third CH2. So I'll put these in colors so that they're a little easier to follow. So this carbon here, this carbon here on the other side of the ester is like this one here. This carbon here is like this one. This third one is like this one. And you can see how that would connect to the carbonyl right there. So the molecule you'd suspect here would be that. That gives us a triplet, a multiplet, all with 2 hydrogens in them, and the shift patterns that we see because of the closeness to the electronegative atoms. And so that would be the molecule you'd expect here. And if you were unsure, you could do IR spectroscopy, and because of this ketone thing, or I should say it's an ester, but the carbonyl there will show up, the carbon to oxygen double bond will show up at around 1700 wave numbers. And so that would let you know, that would be supporting evidence for this structure. Okay, in this next one, they give us the molecular formula. If you were working in a laboratory, you would figure that out by comparing the molecular ion peak and the M+1 peak in the mass spectrum. So first thing we want to do is to figure out the index of hydrogen deficiency. 1/2 times 2 times the number of carbons, we have 9 carbons, plus 2, plus the number of nitrogens, we don't have any, minus the number of halogens, which we don't have any, minus the number of hydrogens, which we have 10 here. And so that's going to be 1/2 18 plus 2 minus 10, so that's 1/2 of 10 which is 5. And remember, if you ever have a hydrogen deficiency index that's 4 or bigger, chances are that you have a benzene ring, right? 4 or bigger means you have a benzene ring, and you can confirm it by looking between 6.5 and 8 in the NMR spectrum. So already we have a really big degree of unsaturation, so we look between 6.5 and 8, and we see we do have peaks. The only thing that would produce peaks between 6.5 and 8 in a proton NMR spectrum is a benzene ring. So we know we have a benzene ring. Now watch out, because a benzene ring only has 4 degrees of unsaturation, 1 ring, and 3 pi bonds. So that's 4, but we have 5. So I'm just going to make a note that we still need either 1 ring or 1 pi bond. Okay, now let's use the integration values to figure out how many branches we have coming off of the benzene ring. So here, the lowest number for the integration values seems like it's 13.9, so I'm going to divide everything by that. And for me, that is giving me around 1 here, and then 21.5 divided by 13.9 is giving me around 1.5 for this next one, around 1 for that, and 1.5 here. So those are the relative values, but they're obviously not the absolute number of hydrogens, because you could never have 1.5 hydrogens. So we'll multiply these to get rid of the 0.5. That would turn them into 2, 3, 2, and 3. So we multiply all those numbers we got at first by 2. So again, these could just be the relative numbers. Let's add them up and see what they give us. 2 plus 3 plus 2 plus 3 gives us 10 hydrogens total. We do have 10 hydrogens, so these numbers are not just the relative numbers, they are the absolute numbers of hydrogens in each of these electronic environments. Now both of these peaks here are coming from the benzene ring. Anything between 6.5 and 8 is coming from the benzene ring. And so the benzene ring has a total of 2 plus 3, or 5 hydrogens. Because benzene without any branches would have 6 hydrogens, having 5 means one of the hydrogens got replaced by a branch. So we know our benzene ring has just 1 branch. Next, we have a quartet, right? This has 1, 2, 3, 4 little spikes. A quartet with an integration of 2, and a triplet, 1, 2, 3 little spikes, with an integration of 3. And that is one of those patterns that I pointed out at the very beginning. That's the pattern for an ethyl group. So if you have a quartet with an integration of 2 and a triplet with an integration of 3, that's a sign that you have an ethyl group. So that tells us we have an ethyl group. Okay, so let's step back, take stock. What have we used so far? What do we have left? We've used 6 carbons plus 2 carbons is 8 carbons, but we have 9, so that means we need to add 1 in. So we have 1 carbon left. We've used 5 hydrogens here, plus another 5 from the ethyl group. We've used 10 hydrogens, and there are only 10 hydrogens, so we've used all of our hydrogens. And finally, we have not used that oxygen, so we still also need to add in the oxygen. And remember, we still need to add in 1 ring or 1 pi bond. Now, if these are our pieces, there's no way we can add a ring here. We would have to add a pi bond. We can't add a pi bond to either of the branches because it would change the splitting patterns. So the pi bond has to go between the carbon and the oxygen. And there's only one way to put those pieces together. You would have the benzene ring connected to the carbon and the carbonyl, and then the ethyl group on the other side. And that would be the structure for that beautiful spectrum there. That's the structure that's revealed by that spectrum. And if you wanted to check in a laboratory, you say you're working at your bench and that's what you came up with. If you wanted to check, you'd do IR and you'd look for the sharp peak at 1700. That would tell you if you had that ketone. All right, next one. So here they give you this molecular formula. In a laboratory, you'd get that by comparing the molecular ion peak to the m+1 peak, the relative heights of those. That would give you, allow you to figure out that molecular formula. And once you have that, find the index, get the NMR spectrum, find the index of hydrogen deficiency, so 2 times the number of carbons, which we have 5 here, plus 2 times, plus the number of nitrogens, which is 0, minus the number of halogens, which is 0 in this molecule, minus the number of hydrogens. So that's 1/2, 12 minus 12, well, that's 0. So we don't have any rings, we don't have any pi bonds in this molecule. Okay, well, let's see. One thing that might help is just to get absolute number of hydrogens for each of those electronic environments. So the smallest integration value I see is 13.6. I'm going to divide each of those numbers by 13.6. This way I can figure out how many hydrogens are in each of these different environments. So this has just 1 hydrogen, at least relatively. This one looks like it would have 2. This one, 84.5 divided by 13.6, that's around 6. And then that last one would be 3. So those are relative numbers. We want to make sure they're absolute numbers. To do that, we'd add them up. So 1 plus 2 plus 6 plus 3 is 12, and the molecule does have 12. So these are not just relative numbers, they're also the absolute numbers of hydrogens in each of these electronic environments. Now notice here you have 1, 2, 3, 4. That's a quartet with 2 hydrogens in it, and you have a triplet with 3 hydrogens in it. That is one of those patterns, the pattern for an ethyl group. So a quartet with 2 hydrogens in it and a triplet with 3 hydrogens in it, that's a sign that you have an ethyl group. So we know that one of our puzzle pieces will be an ethyl group. So that takes care of those 2 signals. Next, we have 6 hydrogens in a singlet. Now, usually when you have multiples of 3, and they're not in any of the patterns that we saw, the ethyl pattern, the isopropyl pattern, or the tert-butyl pattern, it usually means you have methyl groups. So if you have 3 hydrogens in a signal, 6 hydrogens in a signal, 9 hydrogens in a signal, it usually means you have methyl groups. And if they're in singlets, that also supports the fact that they would be in a methyl group, because it's easy to separate a methyl group from the rest of the hydrogens in a compound. So these 6 hydrogens, that's probably 2 methyl groups. So 6 hydrogens. And in order for them to show up in one signal, they have to be attached to the same carbon, because they have to be in the same electronic environment to show up in that same signal. Now, if that were true, what pieces would we have used so far? 2 carbons, 3 carbons, 4 carbons. So we'd only have 1 carbon left. Then we would have used 5 hydrogens plus 3, that's 11 hydrogens. We have 12, so we'd have 1 hydrogen left. And the only other thing we haven't used is an oxygen. So we'd have an oxygen left. So all we'd have left is an oxygen and a hydrogen. There's only one way to put them together. And now there's only one way to put all of these pieces together. And that is to have this carbon in the middle with 4 bonds to those branches. So you'd have that molecule there. And if you were working in a laboratory and you wanted corroborating evidence for that, you would do an IR, you'd run an IR spectrum and you'd look for the alcohol. And the alcohol would have a smooth, broad peak between 3600 and 3200. So a normal person sees this and it's meaningless. You see it, you see a richer world, you see that molecule there. So those are all of our practice problems here for using an NMR spectrum and using that to draw the structure of a molecule when you're given the molecular formula. So definitely commit to memory these patterns here for an ethyl group, an isopropyl group, a tert-butyl group, and also the pattern for having a benzene ring. And the other thing that's useful to keep in the back of your mind is if you have a lot of hydrogens in your molecular formula and very few signals, that's a sign that you have symmetry. And as you do more and more of these practice problems, it'll become more and more straightforward interpreting these spectra.